So in this video, we're going to start off section 6.4, the central limit theorem, by talking about the central limit theorem, which is one of the most celebrated results in probability, because it is actually going to take very little information about what happens when we take a random sample, and we're going to get a lot of information about a sample mean estimator. So the context is this. We have some random sample from a population where we take quantitative measurements and we're going to take a sample mean, but we do this repeatedly. So random samples come from the same distribution independently of each other, and this means that in the long run, when we take more and more of these samples, we get more values for the sample mean, and ultimately these are coming from random outcomes of the sample mean estimator. But we don't need to know anything about the underlying population from which we're drawing these samples, so long as we have a sufficiently large sample size. So what the central limit theorem tells us is it's telling us what the sampling distribution of the sample mean will be in two actually very interesting cases. So this is our context. We are taking random samples of the same size n, and we're taking these from independently and identically. I spelled that wrong. Identically distributed random variables. So this is the scenario that we're drawing here. And if x bar is the sample mean, as long as either the sample size is sufficiently large or the random samples are taken from a normal distribution, then we can actually determine the exact distribution of the sample mean. So x bar is distributed as a normal random variable with mean, so its expected value is the expected value of the original random variables, and the standard deviation is the original standard deviation divided by the square root of n. This sounds a lot like we've already seen. It sounds like a retelling of the theorem from the previous section, but it's actually much stronger because of this condition right here. So previously we said as long as the random samples are taken from a normal distribution, but now so long as we have a large enough sample size, we will always know that we have a normal distribution for the sample mean with a mean equal to the original the original expected value, and the standard deviation is now just divided by the square root of n. And this is true for any distribution that we're taking our sample mean from, which is very powerful. In fact, so powerful that it also doesn't matter if the original random variable is discrete or continuous. So, as an example, we'll work with a random variable here taken from earth science, actually. So, in our example, we have a random variable that represents the number of detected neutrinos, which are these subatomic particles that pass through the Earth at any given moment. They're elementary particles emitted from supernova. And these neutrinos are detected by an array of equipment called Amanda in Antarctica. This has actually since been decommissioned. And we know that the distribution of this random variable, so how many neutrinos are detected at in any given microsecond, is a Poisson random variable with parameter lambda equal to 4. So, two things. For our Poisson distributions, the expected value is the parameter lambda, and the standard deviation is the square root of the parameter lambda, which is in this case 2. Now, a Poisson random variable is discrete, but we suppose we take random samples of size 40 with a replacement from our distribution of detected neutrinos in a randomly selected microsecond. That is, if we have this record, and it's spread out over the last month, 2 months, in any given microsecond, we can capture how many neutrinos were detected there. And that means that the distribution of the sample mean, so in each of these samples we determine a sample mean, that the distribution is going to be normal with a mean equal to 4 and a standard deviation equal to 2 divided by the square root of 40, which is roughly 0.316. So while it's misleading to superimpose a support and the variable that it's taken from, we can sort of visualize the connection between the original random variable and the sample mean. So if this is the original random variable, I'm being fairly imprecise here, although we could actually sit down and calculate the probabilities in each of these bars. So this is the probability mass graph of the Poisson random variable. And our sample mean random variable will be centered at the same peak of 4. So actually this is slightly misleading, sorry. Except it has a much, much lower spread, and we're looking at a density curve rather than the probability mass function graph. So again, not super accurate to superimpose them on the same graph, but we are getting a continuous random variable from a discrete variable. So now we can answer questions about the sample mean very precisely. So for instance, if we have a randomly selected microsecond, since we're measuring in microseconds, what is the probability that we detect no more than 3 neutrinos? So while this is about a specific random outcome, so we're asking a question about x, not x bar. So in other words, we're asking what's the probability that this random variable x is less than or equal to 3, which of course means that we're asking something about the Poisson random variable, okay? So if f Poisson denotes the CDF, or the cumulative density function for the Poisson random variable, then we're interested in evaluating it at 3. And we can use a calculator, so we can use Poisson CDF if we want on a TI-84, or we can use a table too. We could even calculate it by hand if we were so inclined. But we estimate that this is 0.433. Okay. Now the question that we have now is, in a random sample of 40 of these records, what is the probability that the sample mean is no more than 3 neutrinos? Okay, that is terrible. Let me rewrite that. Now we're asking a question about the sample mean. So we need to invoke the distribution of the sample mean, which is a normal distribution with a mean of 4 and a standard deviation of 0.316. So in other words, we can use any of our techniques with working with normal distributions, including standardization. So this is the same as asking about the standard normal distribution. What's the likelihood that it will be less than or equal to 3 minus the mean divided by the standard deviation? And we find that if we compute this, we'll end up with 0.0007. And this is a vastly wild result, and that comes from the fact that with estimating the probability that the detection of no more than 3 neutrinos has to do with the original random variable, we're filling in these areas, whereas we're looking at this area for the distribution of the sample mean, which is vanishingly low, very, very small. Not small enough for us to call it 0, but small nonetheless.